My name is Gunnar Nee, and welcome to the presentation of my thesis project entitled The Design, Integration, and Testing of an Engine Performance Measuring System for the Yanmar 4JH110 Diesel Test Engine at Webb Institute. First, I would like to make some acknowledgments. I would like to thank my principal advisor, Professor Gallagher, for offering his endless knowledge, experience, and time in the lab. I would like to thank machinist Jamie Swan for his effort and patience in the machine shop and Haberly Laboratory. I would also like to thank my reader, Dean Werner, and my editor, Professor Lutz, for their help in developing the written thesis document. I will now begin with an outline of my thesis presentation. First, I will discuss the background and theory pertinent to this project. Second, I will summarize relevant past work conducted as part of previous theses. Next, I will define the thesis objectives. Then we will dive into the manufacturing and build process. And finally, I will discuss testing and results, and we will conclude with recommendations for future work. Moving on to background and theory. Ever since James Watt developed the first practical steam engine, engineers have developed countless methods for quantifying engine performance. First, an engine's capability was expressed by the number of horses it might replace. Then, more useful standards of power were defined. The horsepower in 1782 and the watt a century later. For rotating machinery, including any engine, power output is defined as the torque produced times the rotational speed achieved. Today, torque is generally measured using a dynamometer and is expressed in Newton meters. Rotational speed, omega, is measured using a tachometer and is expressed in radians per second or RPM. By the time Rudolf Diesel introduced his compression ignition internal combustion engine in February of 1897, customers weren't just concerned with how much power an engine could produce, they were concerned with how efficiently that power was delivered. Diesel's early engines could achieve efficiencies greater than 25%, while typical steam engines of the time might struggle to achieve 10% thermal efficiency. One useful metric for evaluating engine efficiency is brake-specific fuel consumption. Brake-specific fuel consumption is defined as the rate fuel is consumed divided by the power produced. The rate of fuel consumption is a mass flow rate expressed in grams per hour. The power produced is expressed in kilowatts. This gives us the units of brake-specific fuel consumption, grams per kilowatt hour. With some clever setup, brake-specific fuel consumption can be calculated using equipment found here at Webb. In fact, multiple Webb theses have been dedicated to determining this metric for a variety of engines. One such setup was developed as part of James Benoit's 2001 thesis entitled The Design, Installation, and Testing of an Engine Measuring System for the Cummins 4BTA 3.9 Diesel Test Engine in Haberly Laboratory. The goal of Benoit's project was to, quote, design and install a system capable of calculating specific fuel oil consumption of the diesel engine in Haberly Laboratory. Benoit was successful, and the system has been a critical part of Webb's ME6 class for the past 2 decades. However, diesel engine technology has advanced significantly since the introduction of the mechanically controlled Cummins engine. This engine has also begun to show signs of age and unreliability. Figure 3 shows Benoit's system, with the Cummins engine on the left, coupled to the Midwest dynamometer. More recently, in 2015, Webb Institute purchased the Yanmar 4JH110 diesel engine, shown in Figure 4, using a grant from the United States Navy. This engine was designed for use in yachts and features an electronically controlled common rail injection system. The system is intended to reduce harmful NOx emissions, which negatively impact the environment and human health. The flexible nature of this more modern, electronically controlled engine would significantly increase students' ability to conduct meaningful experimentation regarding engine efficiency, engine vibrations, and emissions. In 2020, L.J. Bach aimed to use this engine in his thesis entitled Design of a High-Speed Common Rail Diesel Engine Test Platform and Support Systems. Although hindered by the global pandemic, Bach made significant progress in designing a platform and support systems to integrate the Yanmar 4JH110 diesel engine into the existing small diesel engine laboratory. Figure 5 displays Bock's SolidWorks model of the Yanmar engine, custom power takeoff system, and steel foundation. My thesis is a continuation of Bock's work. This brings me to the objectives of my thesis project. The first objective is to assemble an integrated test platform for the Yanmar 4JH110 diesel engine to enable learning exercises and support future experimentation. The second objective is to establish a system and procedure for measuring specific fuel oil consumption of the Yanmar engine. With the objectives defined, we can now move on to the execution of this thesis. The first part of this project involved manufacturing certain custom parts for the Yanmar engine and support systems. One of these parts was a custom drive ring designed as part of Bock's 2020 thesis. Bock's SolidWorks model of the drive ring is shown in Figure 6, and the old SAE specification drive ring is shown in Figure 7. While much of the machining for this part was done in the Webb Institute machine shop, with help from Professor Gallagher and Jamie Swan, the cutting of the internal gear teeth was outsourced to another machine shop. More discussion on the purpose of this drive ring and its installation will be included later in this presentation. Another part we manufactured was a custom dry exhaust fitting to replace the Yanmar supplied wet exhaust system. Figure 8 shows the process of machining the custom exhaust flange on the Bridgeport CNC mill. Figure 9 shows the whole body of the exhaust fitting installed on the Yanmar engine. Here you can see the custom exhaust flange mounted on the Yanmar engine's turbocharger. Figures 10 and 11 show the aluminum bar engine mounts. Note the cuts made to accommodate the width of the flywheel. With the smaller parts manufactured, it was possible to move on to the assembly of the Yanmar engine's foundation, pictured in Figure 12 on the right. This foundation was constructed from a steel base originally designed for a Cummins engine. To accommodate the Yanmar engine, the foundation was augmented with steel I-beams and the aluminum bar mounts mentioned previously. The focus was in making sure the foundation's height was within acceptable tolerance for engine alignment. Once in position, the engine foundation was secured to the concrete laboratory floor. Next, the custom drive ring, designed by Bock as part of his 2020 thesis, was installed on the Yanmar engine's flywheel. The gear ring is pictured in Figure 13 on the right. Again, this drive ring is identifiable by its internal gear teeth. These internal gear teeth mesh the engine's ISO specification flywheel to the SAE specification power takeoff, or PTO. All of the engine's mechanical power is delivered through this ring gear. Finally, the engine was anchored to the foundation and aligned with the input shaft of the dynamometer using laser alignment tools. Figure 14 shows the process of landing the engine on the foundation with a portable crane. The engine support systems, including the cooling system, fuel service system, and instrument and control systems, were then installed. Figure 15 offers a closer look at the laser alignment tools used to align the Yanmar engine and power takeoff with the Midwest dynamometer. Once the laser emitter receivers were secured on the couplings, they are rotated through the 9 o'clock, 12 o'clock, and 3 o'clock positions. The change in the relative distances between the emitter receivers is measured, and this information can be used to align the machines to within a few thousandths of an inch. With this, the assembly of the performance measuring system for the Yanmar 4JH110 diesel engine was complete. From Figure 16, we can identify the major components. The largest components, as seen previously, are the foundation, the actual Yanmar engine, and the Midwest dynamometer. Above the dynamometer are the digital readouts for the dynamometer arm force and tachometer. On the far right is the fuel container and digital scale. This scale is used in conjunction with a timepiece to measure the rate of fuel consumption. With assembly completed, soon came the moment of truth. The Yanmar 4JH110 diesel engine runs on its current installation in Haverly Laboratory. At this point, the engine is ready for testing using the Midwest dynamometer and laboratory instrument board. I'll now describe the performance testing procedure. First, the engine is run at steady state for several minutes. Steady state means constant speed, constant torque, and constant fuel flow rate. While the engine is running at steady state, measurements will be taken. Engine torque is measured using the dynamometer. Engine speed is measured using the tachometer, and fuel flow rate is measured using the digital scale. The previous steps are repeated for a series of torques and speeds. And once the data is collected, output power and brake-specific fuel consumption are calculated. This information can be used to plot a fuel map. Figure 17 is an example of a fuel map developed for a diesel engine similar to the Yanmar engine used in this project. In this case, the x-axis represents RPM, and the y-axis represents effective pressure. The blue contour lines represent bands of constant brake-specific fuel consumption. If you're looking to operate this engine at its most efficient state, you would aim for where brake-specific fuel consumption is minimized, in this case, around 2200 RPM and 15 bar effective pressure. Right here would be your target. Moving on to the results at this time. Early testing revealed deficiencies with the lab central cooling system, and as of Friday, these issues were resolved and preliminary test results were obtained. We are in a position to complete the test matrix in the next few days. So at this point, we can say the Yanmar engine is controllable across its RPM range from 800 to 3200 RPM. The dynamometer and tachometer are functional, and preliminary data for brake-specific fuel consumption has been captured. In conclusion, the Yanmar 4JH110 diesel test engine has been integrated with Webb Institute's small diesel engine lab, thus satisfying the primary objective of this thesis. This electronically controlled engine is ready to enable learning exercises and support future experimentation. The second objective of this thesis has not yet been met, as brake-specific fuel consumption figures are still being collected. I'll now comment on recommendations for future work. First, we recommend comparing the performance and emissions data from the Yanmar 4JH110 engine against the mechanically controlled Cummins 4BTA 3.9. It would also be interesting to explore the effect of injection timing and common rail pressure have on engine performance and emissions. This study could be conducted through the engine's NEMA backbone or using a Yanmar plugin module. This exercise could provide insight into how engineers tune electronically controlled engines to balance the completing goals of maximizing performance while minimizing emissions. Thank you for attending the presentation of my thesis entitled The Design, Integration, and Testing of an Engine Performance Measuring System for the Yanmar 4JH110 diesel test engine at Webb Institute. I would now like to invite Jeff, Kaz, and Abigail up to answer any questions on the topics presented today. Thank you.